Hello. You found Science Blanket, a quiet corner for your mind to rest. Tonight, we are wrapping ourselves in the story of our home, planet Earth. Beyond the cities and the noise, our world is a living miracle, a blue marble suspended in the velvet dark, holding everything we've ever known in a gentle, spinning embrace. Imagine yourself resting in a quiet, sun-drenched clearing, feeling the slow pulse of the ground beneath you. You don't need to navigate the continents or study the deep oceans tonight. Just let the steady gravity of the Earth keep you grounded and safe. If this blanket of wonder helps you find peace, please subscribe so we can keep reaching other sleepy minds. Take a deep breath and let your body sink into your bed. Relax your hands, let your breath find its own natural rhythm, and feel the stillness of the room around you. You are exactly where you need to be. Let's explore the wonders of our planet together. Our home, this pale blue dot suspended in the vastness of space, holds a special place in the cosmic neighborhood. Earth is the third planet from the Sun, nestled between Venus and Mars in a position that turned out to be just right for life as we know it. When you look up at the night sky and see those distant points of light, it's humbling to think that our entire world, with all its mountains and oceans and forests, is just one small sphere orbiting an ordinary star. But what makes this sphere so extraordinary is its story, a story that began unimaginably long ago. About 4.5 billion years ago, in a swirling disk of gas and dust circling our young sun, something remarkable began to happen. Tiny particles started colliding and sticking together, growing larger and larger over millions of years. The same cosmic material that built Mercury, Venus, and Mars also built our Earth. We're made of stardust, quite literally, the remnants of ancient stars that lived and died long before our solar system even existed. This cloud of debris slowly coalesced, pulled together by gravity, heating up from countless impacts until it formed a molten ball that would eventually cool and develop the layered structure we know today. It's a process that required patience on a scale difficult for human minds to grasp, but the result was worth the wait. Now, as we speak, our planet is racing through space at a speed that would make any Earthbound vehicle seem to be standing still. Earth orbits the Sun at approximately 18.5 miles per second. Think about that for a moment. In the time it takes you to draw a single breath, our world has traveled dozens of miles along its cosmic path. We don't feel this motion, of course, because we're moving right along with it, like passengers on the smoothest train imaginable. This swift journey carries us around the Sun once every 365.25 days, which is why we need to add a leap day every 4 years to keep our calendars aligned with the seasons. The distance of our orbit places us in what scientists sometimes call the Goldilocks zone, a region around the Sun where conditions are not too hot and not too cold, but just right. This habitable zone is where temperatures allow liquid water to exist on a planet's surface, and that simple fact has made all the difference for Earth. Too close to the Sun, like Venus, and water would boil away into the atmosphere. Too far away, like Mars, and it would freeze solid. But here, in this perfect middle ground, water can flow and pool and shape the surface in endless ways. It's this liquid water that makes Earth shine blue when seen from space, a color unique among all the planets in our solar system. Water is Earth's signature, its defining feature, the substance that covers most of its surface and fills the air with moisture and possibility. About 71% of Earth's surface is covered by water, leaving less than a third as dry land where continents rise and mountains reach toward the sky. From space, an astronaut would see more blue than brown or green, more ocean than Earth in the planet called Earth. This vast covering of water isn't just decorative. It plays a crucial role in regulating our climate, distributing heat from the equator toward the poles, providing the moisture for rain and snow, and serving as home to countless forms of life that we're only beginning to understand. The total amount of water on our planet is almost impossible to visualize in everyday terms. Earth contains more than 1.4 billion cubic kilometers of water. Imagine a cube of water so large that each edge stretches over 1,000 kilometers, and you'd still need more than 1,000 of those cubes to equal all the water on Earth. Most of this water, about 97%, is salty ocean water, while less than 3% is fresh water that we can drink. And of that small fraction of fresh water, most is locked away in ice caps and glacier, leaving only a tiny portion readily accessible in lakes, rivers, and underground aquifers. When you fill a glass with water, you're drawing from a resource that's both abundant on a planetary scale and precious because so little of it is available for our use. The oceans that dominate our planet's surface aren't all the same size or depth. The Pacific Ocean is the largest and deepest ocean on the planet, so vast that it contains more water than all the other oceans combined. It stretches from the western coasts of the Americas to the eastern shores of Asia and Australia, covering an area larger than all of Earth's land put together. Ancient Polynesian navigators crossed this immense expanse in canoes, reading the stars and waves with knowledge passed down through generations. Today, despite all our technology, much of the Pacific remains unexplored, its depths holding mysteries we're only beginning to uncover. The Pacific isn't just large in area. It also contains the deepest trenches on Earth, places where the seafloor drops away into darkness that sunlight never reaches. Speaking of those depths, the deepest point on Earth isn't the peak of the tallest mountain, but rather a place far below the waves. The Mariana Trench, located in the western Pacific Ocean, plunges nearly 36,000 feet deep, almost 7 miles beneath the surface. If you could place Mount Everest at the bottom of this trench, more than a mile of water would still cover its summit. The pressure at these depths is crushing, more than 1,000 times the atmospheric pressure at sea level, yet life persists even here. Strange creatures adapted to eternal darkness and immense pressure drift through these abyssal waters, reminding us that life on Earth is tenacious and creative beyond our expectations. Only a handful of humans have ever descended to the deepest part of the Mariana Trench, making it in some ways less explored than the surface of the Moon. While we've been discussing the water that flows and covers much of Earth, there's another vast reservoir of water that stays frozen solid for thousands of years at a time. Antarctica, the icy continent at the bottom of the world, contains about 70 to 90% of Earth's freshwater, all locked in ice. The Antarctic ice sheet is so thick in places that it's more than 2 miles deep, an almost incomprehensible amount of frozen water pressing down on the bedrock below. If all this ice were to melt, which would take extraordinary warming sustained over a very long time, sea levels around the world would rise by more than 200 feet, redrawing coastlines and changing the face of human civilization. But under current conditions, Antarctica remains frozen, a vast white wilderness where temperatures can drop far below anything most humans will ever experience. This frozen realm, part of what scientists call the cryosphere, serves an important function in Earth's climate system beyond just storing water. The cryosphere, which includes all the ice and snow on our planet, reflects sunlight back into space, helping to cool the planet. Fresh snow can reflect up to 90% of the sunlight that hits it, compared to darker surfaces like forests or oceans that absorb much more of that energy. This reflective quality means that ice-covered regions act like a planetary thermostat, bouncing solar radiation away before it can warm the surface. It's one of many feedback systems that have kept Earth's climate relatively stable over the long spans of time that allowed complex life to evolve. As you drift towards sleep, imagine those vast ice sheets gleaming white under the polar sun, silently doing their part to maintain the delicate balance that makes our blue planet habitable. Beneath the solid ground where we build our homes and plant our gardens, beneath the deepest ocean trenches and the roots of the oldest mountains, our planet has structure and depth that most of us never think about in our daily lives. Earth has 4 main layers, each one distinct in composition and behavior, like the layers of an onion wrapped around a center. There's the crust, the thin skin we live on. Then the mantle, a thick layer of hot rock that flows slowly over geological time, and deeper still, the core itself, split into 2 parts with very different properties. Understanding these layers helps us make sense of why our planet behaves the way it does, why the ground sometimes shakes, why volcanoes erupt, and why compasses point north. At the very center of our world lies something remarkable and almost contradictory. The inner core is solid iron and nickel, a sphere about the size of the moon, suspended in the middle of the planet by the layers surrounding it. You might expect that something so deep inside Earth, under such tremendous pressure from all the rock above it, would be molten and liquid, but the pressure is so intense at this depth that the metal is actually squeezed into a solid state despite the incredible heat. The temperatures here reach over 5,400 degrees Celsius, hot enough to vaporize almost any substance we encounter on the surface. This solid sphere spins at its own rate, slightly different from the rotation of the planet above it, creating a complexity of motion deep underground that we're still working to fully understand. It's worth pausing to consider just how hot that inner core really is. Earth's core heat exceeds the surface temperature of the Sun. That seems almost impossible when you first hear it, that the center of our relatively small planet could be hotter than the surface of the star that warms us from 93 million miles away. But remember, the Sun's surface, while certainly hot, is much cooler than its interior, where nuclear fusion takes place. Still, the comparison helps us grasp that we're living on the cool, thin skin of what is fundamentally a very hot planet. This internal heat is left over from Earth's formation, from all those impacts that built our world billions of years ago, combined with heat generated by the decay of radioactive elements deep underground. It's an ancient warmth, slowly leaking out over time, that will keep our planet's interior hot for billions of years to come. Surrounding that solid inner core is a layer with very different properties. The outer core is liquid, composed of molten iron and nickel that flows and swirls in complex patterns driven by Earth's rotation and by convection as hotter material rises and cooler material sinks. This motion isn't random or chaotic. It follows patterns influenced by the planet's spin and by the temperature differences within the liquid metal. Scientists call this movement the geodynamo, and it powers one of Earth's most important protective features, its magnetic field. As the electrically conductive liquid iron moves through existing magnetic fields, it generates electric currents, which in turn generate more magnetic field, creating a self-sustaining system that has been operating for billions of years. Without this liquid outer core in constant motion, Earth would be a very different and far less hospitable place. The magnetic field generated by this process does something crucial for life on the surface far above. This magnetic field shields Earth from harmful solar wind, the stream of charged particles constantly flowing out from the Sun in all directions. These particles, if they reach the surface in full force, would gradually strip away our atmosphere and bombard the surface with radiation that would make life very difficult, if not impossible. The magnetic field deflects most of these particles, channeling them around the planet or funneling them toward the poles, where they sometimes interact with our atmosphere to create the beautiful auroras that dance across the sky in far northern and southern latitudes. Mars, which lost its global magnetic field billions of years ago, shows us what happens without this protection. Its atmosphere has been largely stripped away, leaving a cold, dry world with only a thin whisper of air remaining. Earth's magnetic field isn't static and unchanging, though. Over geological time, something strange happens. Earth's magnetic field flips polarity every 200,000 to 300,000 years, though the timing is irregular and unpredictable. During one of these reversals, which can take a few thousand years to complete, the magnetic North Pole and South Pole trade places. Compasses that once pointed north would eventually point south instead. The geological record preserved in rocks shows us evidence of these flips, frozen in minerals that aligned themselves with the magnetic field as they formed. We can read this history like a book, seeing patterns of normal and reverse polarity stretching back through millions of years. Scientists believe we're probably overdue for another flip, though that overdue is on a geological timescale, meaning it could happen tomorrow or 10,000 years from now. Even without a full reversal, the magnetic field is constantly changing in smaller ways. The magnetic North Pole drifts roughly 55 kilometers per year, moving across the Arctic at a pace that has actually been accelerating in recent decades. This drift means that navigation charts need to be updated regularly to account for the changing position of magnetic north. The North Pole that compasses point to has wandered from northern Canada toward Siberia over the past century, following the shifting patterns of flow in the liquid outer core far below. For most of history, this drift didn't matter much, but in our age of GPS and precise navigation, we need to track these changes carefully. There's something almost poetic about it, though. Even the directions we use to orient ourselves are in constant, slow motion, reminding us that nothing on Earth stays exactly the same forever. All this heat trapped inside our planet, left over from its violent birth and sustained by radioactive decay, does more than generate magnetic fields. Without core heat, Earth would have no plate tectonics and likely no life as we know it. That internal heat drives convection currents in the mantle, the thick layer of hot rock between the crust and core. These currents, flowing at speeds measured in centimeters per year, push and pull on the crust above, creating forces powerful enough to move continents, raise mountains, and open ocean basins. On worlds that have cooled down, like Mars or the Moon, this internal engine has stalled, and their surfaces are frozen and unchanging over billions of years. But Earth remains geologically active, constantly reshaping itself, and this activity may have been essential for life to develop and persist. The visible result of all this internal motion is the pattern of cracks and seams covering Earth's surface. Earth's lithosphere, the rigid outer shell that includes the crust and uppermost mantle, is broken into about 15 major tectonic plates, along with dozens of smaller ones. These plates fit together like pieces of a jigsaw puzzle, but unlike a regular puzzle, the pieces are constantly moving. Some plates are colliding, pushing up mountain ranges like the Himalayas. Others are pulling apart, creating rift valleys and new ocean floor. Still others slide past each other horizontally, grinding and catching and suddenly releasing in earthquakes. Standing on solid ground, we usually feel stable and secure, but we're actually riding on one of these plates, drifting across the planet's surface at about the same speed that fingernails grow. This system of moving plates does something remarkable over very long timescales. Plate tectonics recycle Earth's crust over billions of years, taking old seafloor and pushing it down into the mantle where it melts and eventually contributes to new rock that rises through volcanoes or forms new oceanic crust at spreading ridges. This recycling means that Earth's surface is constantly being renewed, that old rocks are returned to the depths and new ones take their place. The oldest seafloor on Earth is only about 200 million years old, a tiny fraction of the planet's age, because older seafloor has already been recycled. Continental rocks can survive longer because they're less dense and don't get pulled down as easily, but even they are eventually worn down by erosion, carried to the seas, and incorporated into new rocks through geological processes. It's a grand cycle of destruction and renewal, operating on timescales so long that it seems static from our brief human perspective, but which keeps our planet dynamic and geologically alive. When we picture Earth in our minds, we often imagine a perfect sphere floating in space, smooth and round like a marble. But reality is a bit more interesting than that simple image. Earth is an oblate spheroid, bulging slightly at the equator and flattened a bit at the poles. This shape comes from the planet's rotation, which creates a centrifugal force that pushes material outward at the equator where the rotational speed is greatest. The difference isn't dramatic enough to notice in everyday life, but it's measurable and significant. The equatorial diameter is about 27 miles greater than the polar diameter, a small difference on a planetary scale, but one that matters for precise calculations of orbits and satellite paths. Our world spins fast enough that it's been stretched into this slightly flattened form, carrying that shape as evidence of its constant rotation. From one side of Earth to the other, passing through the center, the distance measures about 7,918 miles in diameter. To drive that distance at highway speeds without stopping would take weeks. To walk it would take years. Yet from the perspective of the solar system, Earth is a relatively small world, dwarfed by the gas giants Jupiter and Saturn, smaller even than some of their moons. Still, this is the size that turned out to be just right for holding onto an atmosphere thick enough to breathe and support weather, while maintaining enough geological activity to keep the surface dynamic and interesting. A much smaller planet would have lost its air to space and cooled down inside, becoming geologically dead. A much larger planet might have held on to too much atmosphere, creating crushing surface pressure. But this 7,918-mile diameter gives us a world that's comfortable and livable, with room enough for oceans and continents, forests and deserts, mountains and plains. This sphere of rock and metal and water doesn't sit still in space. Earth rotates once every 24 hours, spinning on its axis and producing the rhythm of day and night that governs life on its surface. We've become so accustomed to this cycle that it feels fundamental and unchangeable, the most reliable thing in our experience. The sun rises, crosses the sky, and sets, and then the stars emerge and will overhead until dawn comes again. This rotation also creates the Coriolis effect, which influences wind patterns and ocean currents, making storms spin in characteristic directions and helping to distribute heat around the planet. Every point on the equator is moving eastward at about 1,000 miles per hour, though of course we don't feel this motion any more than passengers on a smoothly sailing ship feel the ship's speed. But even this most reliable of Earth's rhythms is gradually changing. Days on Earth are slowly lengthening by about 1.7 to 2.3 milliseconds per century. The change is tiny, far too small to notice in a human lifetime, but over millions of years it adds up. The main culprit is the Moon, whose gravitational pull creates tides in Earth's oceans. These tides create friction as water moves across the seafloor and against coastlines, and that friction gradually slows Earth's rotation. Meanwhile, the same tidal forces are causing the Moon to slowly drift away from Earth at about 1.5 inches per year. It's a gentle exchange of energy and momentum between two bodies locked in gravitational partnership, playing out over timescales that make human history seem like a brief flicker. Looking back into Earth's deep past, we can calculate how fast the planet used to spin. A day was once only about 22 hours long, back when Earth was young and the Moon was much closer. Ancient corals, which lay down daily growth rings much like trees lay down annual rings, provide physical evidence of this faster rotation. By counting the growth rings in fossil corals hundreds of millions of years old, scientists can determine how many days were in a year back then. The year has always been the same length, determined by Earth's orbit around the Sun, but more days fit into that year when each day was shorter. It's a remarkable piece of detective work, reading the calendar of the ancient past in the structure of long-dead sea creatures, and it confirms what the physics predicted. Our planet has been gradually slowing down, and will continue to do so for billions of years to come. The way Earth spins isn't just about the speed, the angle matters enormously too. Earth tilts 23.5 degrees on its axis relative to the plane of its orbit around the Sun. This tilt is responsible for the seasons that structure the year in most parts of the world. When the northern hemisphere tilts toward the Sun, it receives more direct sunlight and experiences summer, while the southern hemisphere, tilted away, experiences winter. 6 months later, the situation reverses. Without this tilt, the Sun would always be directly overhead at the equator and would never rise more than partway up the sky at higher latitudes. The poles would be locked in permanent twilight, and the equator would receive intense sun year-round with no variation. Instead, this 23.5 degree tilt gives us the beautiful progression of seasons, the lengthening and shortening of days, the migrations of birds and blooming of flowers timed to the Sun's changing angle in the sky. This axial tilt does something else important that we might not immediately think about. That axial tilt allows viable photosynthesis across latitudes, making much more of Earth's surface productive and habitable. If Earth spun upright with no tilt, only the tropical regions would receive enough sunlight to support abundant plant life year-round. Higher latitudes would be locked in permanent coolness with weak sunlight arriving at a low angle. But because of the tilt, even far northern and southern regions receive intense summer sunlight for part of the year, allowing forests to grow well beyond the tropics and enabling seasonal bursts of growth that support diverse ecosystems. The Arctic tundra explodes with life during its brief summer. Temperate forests flourish through spring and summer before going dormant in winter. This seasonal variation, driven by axial tilt, creates ecological niches and opportunities that a non-tilted world would never have. Earth's gravity, which holds us firmly to the ground and keeps the atmosphere from drifting away into space, isn't quite uniform across the planet's surface. Gravity varies slightly across Earth due to uneven mass distribution. Places where dense rock lies close to the surface have slightly stronger gravitational pull. Places where the crust is thinner or where less dense materials dominate have slightly weaker pull. Mountains add mass and increase local gravity slightly. Ocean trenches, where the crust is thinnest, show reduced gravity. These variations are small, just fractions of a percent, but they're measurable with sensitive instruments and they affect satellite orbits in predictable ways. Scientists have created detailed maps of Earth's gravitational field, revealing the hidden distribution of mass beneath the surface. It's another reminder that even something as apparently simple and universal as gravity has subtle complexities when you examine it closely enough. Deep inside the planet, the iron core that generates our magnetic field has its own peculiar behavior. Earth's core rotates faster than the surface, spinning independently at a slightly different rate. The solid inner core can do this because it's surrounded by liquid outer core, allowing it to move separately from the mantle and crust above. The difference in speed is small, perhaps a fraction of a degree per year, but over time the inner core gets ahead of the surface rotation, making a complete extra revolution every few hundred years. This superrotation was predicted by models of Earth's interior and later confirmed through careful analysis of seismic waves passing through the planet. It's strange to think that the very center of our world is spinning faster than we are, racing ahead down there in the darkness and heat, a hidden dancer following a slightly different rhythm. Finally, Earth isn't quite the closed system we might imagine. While the planet formed billions of years ago and most of its mass has been here ever since, we're still accumulating a little bit more material from space. Earth gains about 100 tons of space dust every day, tiny particles left over from comets and asteroids, remnants of the solar system's formation drifting through space. This dust gently rains down through the atmosphere, usually burning up as meteors or settling slowly to the surface as microscopic grains. 100 tons sounds like a lot, but spread across the entire surface of Earth it's an almost invisibly thin layer. Still, over millions of years it adds up. Ancient seafloor sediments contain these cosmic particles, giving scientists a way to study the history of dust falling from space. It's a gentle reminder that Earth remains connected to the solar system around it, still accreting material after all this time, still growing by the tiniest amount each day as stardust settles onto its surface. When we look up at the night sky, one object stands out above all others, brighter and larger than any star or planet visible to the naked eye. Earth has one moon, a natural satellite that orbits our planet at an average distance of 238,855 miles away. This distance isn't constant. The moon's orbit is slightly elliptical, so it comes closer and moves farther away in a regular cycle, but that 250,000-mile average gives us a sense of the gap between our two worlds. The moon is large enough and close enough to show a disk to the naked eye, to display phases as its position relative to the sun changes, to pull on Earth's oceans and create tides. Many planets have moons, of course. Mars has 2 tiny ones. Jupiter and Saturn have dozens, some larger than the planet Mercury. But our moon is special in its relationship to Earth, unusually large compared to the planet it orbits, and intimately connected to our world's history. That connection goes back to a catastrophic event early in Earth's history. The moon formed after a massive collision with a body called Theia, a Mars-sized protoplanet that was sharing Earth's orbital path around the young Sun. About 4.5 billion years ago, in the chaotic early days of the solar system when planets were still forming and orbits were still stabilizing, Theia slammed into the proto-Earth at an angle. The impact was devastating, vaporizing rock, melting both bodies, and throwing enormous amounts of material into orbit around what remained of Earth. This debris disk, made of vaporized and molten rock from both Earth and Theia, gradually coalesced into the moon we see today. Evidence for this giant impact hypothesis comes from many sources. The moon's composition closely matches Earth's mantle. Moon rocks brought back by Apollo astronauts show chemical similarities to Earth, and computer simulations show that such an impact could produce a moon with the size and orbit we observe. That ancient collision did more than create the moon. That impact also influenced Earth's spin and axial tilt, giving our planet the 23.5-degree tilt we talked about earlier and possibly speeding up its rotation. Without the Theia impact, Earth might spin at a different angle or at a different rate, which would mean different seasons or different length days, or perhaps no significant seasons at all. The Moon's subsequent gravitational influence has helped stabilize that axial tilt over billions of years, preventing it from varying wildly as Mars's tilt does. Some scientists think this stability has been crucial for the development of complex life, because it means Earth's climate has varied within certain bounds rather than swinging between extremes. So, in a sense, we owe a debt to that long-ago disaster that nearly destroyed the early Earth. Out of chaos and destruction came a partnership between planet and moon that has shaped everything that followed. Our moon is a permanent companion, but it's not Earth's only satellite, at least not always. Earth occasionally captures temporary minimoons, small asteroids that wander close enough to be pulled into orbit around our planet for a few months or years before escaping again. These objects are typically just a few meters across, far too small and dim to see without powerful telescopes, and they come and go without most people ever knowing they were there. Astronomers have confirmed several of these temporary captures in recent years as telescope technology has improved. One known minimoon orbited Earth for about a year before continuing on its way through the solar system. These brief visitors remind us that space near Earth isn't empty, but filled with debris left over from the solar system's formation, most of it harmless but all of it following the mathematical rules of gravity and orbital mechanics. Beyond these temporary captures, Earth has an even stranger class of companion objects. It also hosts quasi-satellites that orbit the Sun while staying near Earth, locked in orbital resonance that keeps them in our cosmic neighborhood even though they're not actually orbiting our planet. These objects follow paths that mirror Earth's orbit, sometimes getting closer and sometimes farther away, but always remaining relatively nearby from a solar system perspective. One such quasi-satellite has been following Earth for thousands of years and will continue to do so for thousands more before orbital mechanics eventually pull it away. From our perspective, these objects seem to dance around Earth in complex looping patterns, though they're really just following their own orbits around the Sun, orbits that happen to synchronize with ours in peculiar ways. They're a reminder that orbits and gravitational relationships in the solar system can be subtle and strange, not just the simple ellipses we learn about in school. Earth has other features that few people know about, structures so tenuous they're almost not there at all. Earth has a faint ring of sodium created by vaporizing meteors, a gossamer torus of glowing atoms encircling the planet. As meteoroids enter Earth's atmosphere at tremendous speeds, they heat up and vaporize, and some of that vaporized material contains sodium from the meteoroid's composition. These sodium atoms get caught in Earth's magnetic field and form a faint ring that can be detected with specialized equipment. It's nothing like the spectacular rings of Saturn, which are made of ice and rock and are bright enough to see across the solar system. Earth's sodium ring is so faint it was only discovered in recent decades, and you certainly can't see it without instruments. But it's there nonetheless, a delicate structure created by the constant rain of space debris burning up in our atmosphere, a ring made not of ice or rock but of individual atoms torn from disintegrating meteoroids. Our neighborhood in the solar system has a guardian, though it's not close by. Gas giants like Jupiter help shield Earth from frequent impacts by deflecting or capturing comets and asteroids that might otherwise reach the inner solar system. Jupiter's enormous gravitational field acts like a cosmic vacuum cleaner, attracting objects that wander too close and either pulling them into orbit, sending them crashing into Jupiter itself, or slinging them away into different trajectories. The famous Shoemaker-Levy 9 comet provided a dramatic example when it broke apart and slammed into Jupiter in 1994, giving astronomers a vivid demonstration of Jupiter's protective role. Without Jupiter's presence, Earth would likely experience far more impacts from large objects, making life's evolution more difficult and chaotic. It's one of many ways that Earth's position in the solar system turned out to be fortunate, protected by a giant planet far enough away not to disrupt our orbit but close enough to intercept many potential threats. Of course, Jupiter hasn't stopped all impacts, and Earth's surface and biological history bear the scars of those cosmic encounters that did get through. Bolides, large meteorites, and glaciations have acted as evolutionary reset buttons throughout Earth's history, causing mass extinctions that wiped out dominant species and gave opportunities for survivors to diversify and fill empty ecological niches. The most famous of these reset events killed the dinosaurs 66 million years ago, when a 6-mile-wide asteroid struck what is now Mexico's Yucatan Peninsula. The impact threw up so much dust and debris that sunlight was blocked for months or years, causing global cooling and collapse of food chains. 3/4 of all species went extinct, including all non-avian dinosaurs. But from the ashes of that catastrophe, mammals, which had been small and marginal during the age of dinosaurs, diversified and eventually gave rise to primates and humans. Ice ages, too, have forced dramatic changes in life on Earth, expanding and contracting habitats, isolating populations that then evolved independently, and favoring species that could adapt to changing conditions. The remarkable thing about Earth is that it keeps a record of all these events, a library written in stone. Earth records its own history in layered rocks, with older layers generally lying beneath younger ones, creating a chronology that can be read if you know how. Sedimentary rocks form as particles settle out of water or air, accumulating layer by layer over time. Volcanic eruptions leave distinctive ash layers that can be dated and correlated across wide regions. Impact events leave signatures in the rock record, including unusual minerals that form only under extreme pressure and temperatures. Fossils preserved in these layers show us what life was like at different times, revealing the appearance and disappearance of species, the evolution of new body plans, the spread of life from oceans to land. Reading this record requires patience and skill, but geologists have become remarkably good at it, piecing together the story of our planet from fragments of stone scattered across continents. To make sense of this vast history, scientists have divided it into manageable chunks. The geologic timescale divides Earth's 4.54 billion year history into eons, eras, periods, and smaller units, each defined by characteristic rock types or fossil assemblages or major events. The largest divisions are the eons: the Hadean, when Earth was newly formed and hellishly hot; the Archean, when the first life appeared; the Proterozoic, when oxygen began accumulating in the atmosphere; and the Phanerozoic, the current eon, which began about 540 million years ago and is characterized by abundant complex life. These eons divide further into eras and periods with names that might be familiar from school. The Cambrian, when complex animals first appeared; the Carboniferous, when vast coal swamps covered the continents; the Jurassic, when dinosaurs dominated; the Quaternary, which includes all of human history. Each division represents a chapter in Earth's story, and learning to read this timeline gives us perspective on how old our planet really is and how recent our own appearance has been in the grand scheme of things. The invisible ocean of air surrounding our planet, the atmosphere we breathe with every breath, has a composition that makes life as we know it possible. Earth's atmosphere is about 78% nitrogen and 21% oxygen, with the remaining 1% made up of argon, carbon dioxide, water vapor, and trace amounts of other gases. This particular mixture didn't exist when Earth first formed. The early atmosphere was very different, composed mostly of water vapor, carbon dioxide, and other volcanic gases, with little or no oxygen. The oxygen we breathe today accumulated slowly over billions of years, produced by photosynthetic bacteria and later by plants, gradually transforming the atmosphere into something that could support animals like us who need oxygen to survive. Nitrogen, the most abundant gas, is relatively inert and serves mainly as a diluting agent, keeping the oxygen concentration from getting too high. Pure oxygen would make everything dangerously flammable, but mixed with nitrogen at this ratio, the air supports combustion at a safe and sustainable level. High above the surface, in a layer of the atmosphere called the stratosphere, a special form of oxygen does important work protecting life below. The ozone layer absorbs 97 to 99% of harmful ultraviolet radiation from the sun. Ozone molecules, made of 3 oxygen atoms bonded together instead of the usual 2, are particularly good at absorbing UV light. When UV photons hit ozone molecules, the energy breaks the molecules apart, but new ozone forms from the free oxygen atoms, creating a continuous cycle of destruction and regeneration. Without this protective layer, UV radiation would reach the surface at intensities that would damage DNA in living cells, causing mutations and making life on land very difficult. The discovery in the 1980s that certain human-made chemicals were destroying the ozone layer led to the Montreal Protocol, an international agreement to phase out those harmful substances. It's one of the few environmental success stories, a case where humanity recognized a problem and acted quickly enough to prevent catastrophe. The ozone layer is slowly recovering, a process that will take decades to complete, but that demonstrates we can heal damage we've caused. The atmosphere doesn't just protect us, it also gives the sky its color. The atmosphere scatters blue light, giving the sky its color during the day and creating the oranges and reds of sunrise and sunset. When sunlight enters the atmosphere, it encounters air molecules that are much smaller than the wavelengths of visible light. These tiny molecules scatter short wavelengths, the blues and violets, much more effectively than longer wavelengths like red and orange. Blue scatters about 10 times more than red. So as sunlight passes through the atmosphere, blue light gets scattered in all directions, filling the sky with blue from every angle. We see violet less than blue, even though it scatters even more, because our eyes are less sensitive to violet and because some of the violet gets absorbed by the upper atmosphere. During sunrise and sunset, when sunlight passes through much more atmosphere to reach our eyes, most of the blue has been scattered away in other directions, leaving the reds and oranges to dominate. On the moon, where there's no atmosphere, the sky is always black and stars are visible even in daytime. It's the air itself, the invisible gases we barely think about, that paints the sky blue. Within this atmosphere, tremendous energies are constantly at work. Lightning strikes Earth about 8.6 million times per day, roughly 100 strikes every second somewhere on the planet. Each bolt is a massive electrical discharge, a breakdown of the insulating properties of air, allowing millions of volts to leap between clouds or between cloud and ground. Lightning can heat the air in its path to temperatures 5 times hotter than the surface of the sun, causing the air to expand explosively and creating the thunder that follows. Most lightning occurs within clouds or between clouds, never reaching the ground, but the bolts that do strike Earth can carry currents of tens of thousands of amperes, enough to vaporize metal, explode trees, and start fires. Ancient peoples saw lightning as the weapons of gods, and it's not hard to understand why. Even today, with our scientific understanding of electrical discharge, lightning remains dangerous and awe-inspiring, a reminder that the atmosphere holds tremendous energy. The systems that generate all this lightning are themselves impressive in scale. Over 2,000 thunderstorms occur worldwide every day, concentrated in tropical regions where warm, moist air creates ideal conditions for convection and storm development. These storms are nature's way of redistributing energy, transporting heat from the surface up into the atmosphere and converting water vapor into rain. Each storm is a complex, dynamic system with updrafts and downdrafts, ice crystals and water droplets colliding and separating to build up electrical charge. From space, thunderstorms appear as towering clouds that punch through the lower atmosphere into the stratosphere, their tops spreading out into the characteristic anvil shape as they reach altitudes where the air becomes more stable. Inside these storms, winds can exceed 100 miles per hour, hail can grow to the size of baseballs, and the violence of the motion can spawn tornadoes. Yet from a distance, they're beautiful, sculptural forms made of water and ice and air, lit from within by lightning. Lightning doesn't only occur during traditional thunderstorms. Lightning can even erupt from volcanic plumes, a phenomenon called volcanic lightning or dirty thunderstorms. When a volcano explosively erupts, it throws enormous quantities of ash, rock fragments, and volcanic gases high into the atmosphere. These particles collide with each other in the turbulent plume, transferring electrons and building up electrical charge just as ice crystals do in a thunderstorm. When the charge separation becomes large enough, lightning arcs through the ash cloud, creating spectacular displays that early observers sometimes interpreted as signs of divine anger. Modern cameras have captured stunning images of volcanic lightning, showing multiple bolts illuminating the ash cloud from within. It's yet another example of how electrical phenomena pervade Earth's atmosphere, appearing wherever conditions allow charge to separate and accumulate. Among all the various forms of lightning, one remains particularly mysterious and rare. Ball lightning appears rarely as glowing plasma orbs, luminous spheres that float through the air, sometimes passing through windows or walls, lasting for seconds or occasionally minutes before disappearing. For many years, scientists debated whether ball lightning even existed or whether it was just misidentification of regular lightning or optical illusions. But enough reliable eyewitness accounts accumulated, including reports from pilots, scientists, and other credible observers, that it became clear something real was happening. Only recently have researchers begun to understand what ball lightning might be, possibly a form of plasma sustained by chemical reactions or by energy stored in the air's electric field. It remains one of the least understood atmospheric phenomena, a reminder that even in our modern age, nature still holds mysteries that elude easy explanation. The atmosphere produces phenomena beyond the visible and dramatic. Earth emits a continuous low-frequency hum from ocean waves, a constant background vibration that seismometers can detect anywhere on the planet. Ocean waves, driven by wind, transfer energy to the seafloor when they crash and break. This energy propagates through Earth as very low-frequency seismic waves, typically around 3 to 10 MHz, far below what human ears can hear. The amplitude is tiny, less than the width of an atom, but sensitive instruments can pick it up even thousands of miles from any ocean. This hum is always present, a constant bass note that the planet sings to itself, generated by the endless motion of the seas. Scientists studying this hum can learn about ocean conditions and wave patterns, and they have to account for it when searching for other seismic signals. It's strange to think that even when everything seems quiet and still, the Earth is vibrating gently, humming with the accumulated energy of waves breaking on distant shores. The water that falls from the sky carries more than just moisture. Rain contains trace amounts of vitamin B12, synthesized by bacteria living in clouds and in soil that gets picked up by wind and carried into the atmosphere. The amounts are tiny, nowhere near enough to provide nutritional benefit, but the presence of this essential vitamin in rainwater suggests interesting connections between atmospheric chemistry, microbiology, and the cycling of nutrients through the environment. B12 is one of the more complex vitamins, produced only by certain bacteria and archaea, never by plants or animals. That it appears in rainwater at all speaks to the incredible dispersal of microscopic life, bacteria living in clouds and droplets, metabolizing and reproducing in the sky itself. Rain isn't just pure water. It's a dilute solution of dissolved gases, minerals, organic compounds, and living microorganisms, a medium through which materials cycle between sky and earth. Snow, too, has its peculiarities and extremes. The largest snowflake recorded was about 15 inches wide, reported in Montana in the late 1800s. Most snowflakes are much smaller, typically less than half an inch across, but under ideal conditions of temperature and humidity, crystals can grow much larger and even clump together into aggregates of remarkable size. A 15-inch snowflake is hard to imagine, more like a delicate plate of ice than the individual crystals we usually think of. Records from that era are harder to verify than modern measurements would be, but the physics allows for very large snowflakes under the right circumstances. Each snowflake begins as a tiny ice crystal forming around a nucleus, perhaps a speck of dust or pollen, high in a cloud where temperatures are below freezing. As water vapor deposits onto this crystal, it grows, developing the characteristic six-fold symmetry that comes from the hexagonal structure of ice. The exact shape depends on temperature and humidity during growth, which is why every snowflake's journey produces a unique final form. Billions upon billions of these ice crystals fall every time it snows, each one a tiny sculpture created by physics and chance, most of them melting away unnoticed, but all of them part of the water cycle that connects atmosphere, land, and sea. Among all the worlds we've discovered in our solar system and beyond, circling other stars in distant reaches of the galaxy, Earth holds a distinction that makes it precious beyond measure. Earth is the only known planet that supports life. We've found planets in the habitable zones of other stars, worlds where temperatures might allow liquid water, and we've discovered moons in our own solar system with subsurface oceans. But nowhere else, despite decades of searching with increasingly sophisticated instruments, have we found definitive evidence of life. This doesn't mean Earth is unique in hosting life. The universe is vast and we've only examined a tiny fraction of it. But it does mean that life, at least complex life that leaves detectable signs, is rare enough that we haven't found it yet despite looking. This makes our living world special, a place where chemistry became biology, where molecules began to reproduce and evolve, where consciousness eventually emerged to contemplate its own origins. The story of life on Earth is longer than most people realize, but also shorter in certain ways. Life appeared surprisingly late in one sense. Animals exist only in the last 15% of Earth's history. For the first 4 billion years of Earth's existence, life was exclusively microscopic. Bacteria and later more complex single-celled organisms dominated the planet, living in oceans and eventually on land, but remaining invisible to any hypothetical observer who might have visited. The first animals, simple soft-bodied creatures that left few fossils, appeared around 600 million years ago. Before that, for roughly 85% of Earth's history, there were no animals at all, no creatures with eyes or brains or limbs. This perspective is humbling. The dinosaurs, which seemed to dominate Earth for an impressively long time, existed for only about 4% of the planet's history. Humans have been around for less than 1/10 of 1%. We're newcomers on a stage that operated for billions of years before we arrived. The emergence of complex life required specific innovations at the cellular level. Eukaryotic cells, the kind that make up plants, animals, and fungi, emerged from specific chemical conditions billions of years ago, probably through a process where one simple cell engulfed another and the two began living in symbiosis. The mitochondria in our cells, the organelles that produce energy, were once free-living bacteria that took up residence inside other cells. This merger created cells capable of much more complex chemistry and organization than simple bacterial cells could achieve. It's one of the most important events in the history of life, yet it apparently happened only once, or at least all eukaryotes alive today seem to descend from a single common ancestor in which this merger occurred. For billions of years after life first appeared, this crucial step didn't happen. When it finally did, it opened up possibilities for multicellular life, for organisms with specialized tissues and organs, for the incredible diversity of complex life we see today. Another innovation that proved crucial was a new way of reproducing. Sexual reproduction, where genes from two parents combine to create offspring, likely accelerated biological complexity by allowing beneficial mutations from different lineages to combine and by purging harmful mutations more efficiently. Organisms that reproduce asexually pass on exact copies of their genes, barring the occasional random mutation. Sexual reproduction shuffles the genetic deck with each generation, creating variation that natural selection can act upon. This variation allows populations to adapt more quickly to changing environments and probably accelerated the evolution of complex traits that require multiple genes working together. The costs of sexual reproduction are significant, including the need to find mates and the fact that only half your genes go into each offspring, yet the benefits apparently outweigh these costs. Most complex organisms reproduce sexually, suggesting that this innovation was key to the development of biological complexity. Once the basic toolkit for complex life was in place, something remarkable happened in a geologically brief period. The Cambrian explosion, beginning about 540 million years ago, rapidly diversified animal life over the course of perhaps 20 million years. Before the Cambrian, animals were simple and left few fossils. Suddenly, in the Cambrian rocks, we find fossils of creatures with hard shells, compound eyes, jointed legs, and predatory adaptations. Most of the major animal body plans we see today appeared during this relatively short window. The famous Burgess Shale fossils from Canada preserve a menagerie of weird and wonderful Cambrian creatures, showing the experimentation that occurred as animals filled newly available ecological niches. Scientists debate what triggered the Cambrian explosion. Possibilities include rising oxygen levels, the evolution of predation creating an evolutionary arms race, or changes in ocean chemistry that allowed animals to build shells and skeletons. Whatever the causes, this period transformed life on Earth and set the stage for all subsequent animal evolution. The chemistry that makes life possible isn't random or universal. Earth's chemistry perfectly supports complex life processes in ways that might not be replicable everywhere in the universe. Water is an ideal solvent for biochemistry. Carbon forms the backbone of all biological molecules, and the abundance of elements like nitrogen, phosphorus, and sulfur in Earth's crust and oceans provides the raw materials life needs. The pH of the oceans, the temperature range at Earth's surface, the availability of energy from sunlight and chemical reactions, all of these factors fall within ranges that allow complex chemistry to operate. Life didn't just passively accept these conditions, it also shaped them. Photosynthetic organisms transformed the atmosphere by producing oxygen. Life affects the weathering of rocks and the cycling of elements. Earth and life have co-evolved over billions of years, each shaping the other, creating a system where the living and non-living parts of the planet are deeply intertwined. One of the key features that makes Earth's chemistry support life is its water cycle. Earth's hydrosphere, the sum of all water on the planet, enables a unique carbon cycle that regulates climate over geological timescales. Carbon dioxide dissolves in rainwater, forming weak carbonic acid that weathers rocks and carries dissolved minerals to the ocean. Marine organisms use these minerals to build shells and skeletons of calcium carbonate. When they die, these structures settle to the seafloor, eventually forming limestone. Plate tectonics carry this limestone down into the mantle at subduction zones, where heat and pressure release the carbon dioxide, which returns to the atmosphere through volcanoes. This cycle, operating over millions of years, acts as a thermostat for the planet. If temperatures rise, weathering speeds up, pulling more carbon dioxide from the atmosphere and eventually cooling the climate. If temperatures fall, weathering slows, volcanoes continue adding carbon dioxide, and the climate warms again. Without liquid water cycling between ocean, atmosphere, and land, this regulatory system wouldn't work, and Earth's climate might have diverged to extremes like Venus or Mars. Hidden in the oceans, invisible to casual observers, are organisms doing work that sustains the entire planet. Phytoplankton, microscopic photosynthetic organisms drifting in the sunlit surface waters, produce most of Earth's oxygen, more than all forests and grasslands combined. These tiny organisms, including bacteria called cyanobacteria and single-celled algae, use sunlight to split water molecules and fix carbon dioxide into organic compounds, releasing oxygen as a byproduct. Every other breath you take comes from phytoplankton in the ocean. Their populations fluctuate with seasons and ocean currents, blooming when conditions are right and crashing when nutrients run out. From space, large phytoplankton blooms appear as swirls of color in otherwise blue ocean water, visible evidence of the vast productivity happening in the seas. These organisms form the base of the marine food web, feeding zooplankton, which feeds small fish, which feed larger fish, supporting entire ecosystems and the human fisheries that depend on them. In tropical waters around the world, life has built structures so large they're visible from space. Coral reefs are the largest living structures on Earth, created by countless tiny animals called coral polyps working in partnership with photosynthetic algae living in their tissues. Each polyp secretes a skeleton of calcium carbonate, and over thousands of years, these skeletons accumulate into massive reef structures. Australia's Great Barrier Reef stretches over 1,400 miles, a complex of thousands of individual reefs supporting incredible biodiversity. Coral reefs cover less than 1% of the ocean floor but provide habitat for about a quarter of all marine species. They're like underwater rainforests, hotspots of diversity and productivity in waters that would otherwise support relatively little life. Reefs also protect coastlines from storm surge and erosion, and they've been important to human cultures for thousands of years. Unfortunately, coral reefs are sensitive to temperature and ocean chemistry changes, and many reefs around the world are under stress from warming waters and ocean acidification. Their fate in the coming decades will tell us much about how Earth's living systems respond to rapid environmental change. On land, one ecosystem stands out for its role in planetary processes. The Amazon rainforest plays a major role in atmospheric cycling, producing oxygen, absorbing carbon dioxide, and releasing vast quantities of water vapor into the atmosphere. The Amazon contains about 10% of all species on Earth, an almost incomprehensible diversity of plants, animals, and microorganisms living in complex relationships. Trees in the Amazon don't just passively absorb carbon dioxide, they actively influence rainfall patterns. Water evaporating from leaves rises into the atmosphere and forms clouds, which produce rain that falls back on the forest. Some of this water cycles through the forest multiple times before eventually reaching the Atlantic Ocean. The Amazon even produces organic compounds that serve as cloud condensation nuclei, essentially making the seeds around which cloud droplets form. This means the forest partially creates its own weather, a striking example of how life doesn't just adapt to environment but actively shapes it. Losing the Amazon would affect not just the incredible biodiversity it contains, but also atmospheric composition and regional climate patterns across much of South America and beyond. The diversity of life on our planet is staggering when you try to comprehend its full scope. Earth hosts over 8.7 million animal species, though that number is just an estimate and many scientists think the true total could be higher. We've formally described and named perhaps 2 million species so far, meaning the vast majority remain unknown to science, living in remote forests, deep oceans, or simply overlooked in places we thought we'd already explored thoroughly. Each species represents a unique solution to the challenge of survival, a distinct way of extracting energy from the environment and passing genes to the next generation. Some are large and charismatic, the elephants and tigers that capture our imagination. But most are small, the beetles and ants and mites that outnumber larger creatures by incomprehensible margins. In a single handful of healthy soil, you might find more individual organisms than there are humans on Earth, representing hundreds or thousands of species, most of them unknown and unnamed, quietly doing the work of decomposition and nutrient cycling that keeps ecosystems functioning. Even that incredible diversity of animals pales compared to the abundance of life's smallest forms. There are more viruses on Earth than stars in the observable universe. Viruses exist in virtually every environment, from ocean water to soil to the air we breathe. A single drop of seawater can contain millions of viral particles. Unlike bacteria and other cells, viruses aren't technically alive by most definitions, since they can't reproduce on their own but must hijack the machinery of living cells. Yet they play enormous roles in ecosystems, infecting bacteria and other organisms, transferring genes between species, and influencing the evolution of everything they touch. Most viruses don't infect humans and pose no threat to us. They're simply part of Earth's microbial ecosystem, a vast invisible realm of biological entities whose total numbers exceed anything else on the planet. If you collected all the viruses on Earth and laid them end to end, they would stretch for 100 million light-years, far beyond our galaxy and deep into intergalactic space. Among all Earth's creatures, few are as remarkably resilient as the tardigrades. These microscopic animals, typically less than a millimeter long and sometimes called water bears or moss piglets, survive vacuum, radiation, and extreme temperatures that would kill almost any other complex organism. Tardigrades can enter a state called cryptobiosis, essentially shutting down their metabolism and losing nearly all the water in their bodies, becoming dried husks that can survive for years or even decades. In this state, they've been exposed to the vacuum and radiation of space and revived when returned to Earth and given water. They can survive temperatures near absolute zero and temperatures above boiling. They can withstand pressures 6 times greater than those in the deepest ocean trenches. When conditions improve, they rehydrate and resume normal life as if nothing had happened. Scientists study tardigrades to understand the limits of life and the mechanisms that allow survival in extreme conditions. These tiny creatures remind us that life, once established, is remarkably difficult to completely eradicate. Tardigrades aren't the only organisms thriving in conditions we once thought incompatible with life. Extremophiles, microorganisms adapted to harsh environments, thrive in boiling, acidic, and radioactive environments that would be instantly lethal to humans. Bacteria have been found living in hot springs where temperatures exceed the boiling point of water, surviving because the high pressure prevents the water from boiling. Others live in battery acid, in lakes with pH levels that would dissolve human tissue. Some bacteria even thrive in the cooling water of nuclear reactors, where radiation levels would kill any complex organism within minutes. These extremophiles aren't rare exceptions but are abundant wherever their preferred conditions exist. They've expanded our understanding of where life can survive and raised interesting possibilities about life on other worlds. If bacteria can live in Earth's most extreme environments, perhaps similar organisms exist in the subsurface oceans of Jupiter's moon Europa, or in the acidic clouds of Venus, or in environments we haven't even imagined yet. Earth's oceans host creatures of almost mythical proportions. Blue whales are larger than any dinosaur that ever lived, the largest animals to ever exist on this planet as far as we know. An adult blue whale can reach 100 feet in length and weigh 200 tons, equivalent to about 30 elephants. Their hearts alone weigh as much as a car, and their arteries are wide enough that a small child could crawl through them. They feed on some of the smallest animals in the ocean, tiny shrimp-like krill, filtering tons of them from the water with baleen plates in their mouths. Blue whales nearly went extinct due to whaling in the 20th century, reduced to just a few thousand individuals worldwide, but protection has allowed their numbers to slowly recover. To see a blue whale surface, to watch that enormous bulk breach and fall back with a splash that can be heard for miles, is to witness something that seems to defy the limits of biology. That Earth's oceans are deep and productive enough to support creatures of such immense size is itself remarkable. The deep ocean contains creatures as strange as any from science fiction. Bigfin squid, encountered only rarely by deep-sea submersibles, have tentacles that can reach 20 to 26 feet long, held at odd angles as the squid drifts above the seafloor like some alien spider. These squid have been filmed but never captured, and much about their biology remains mysterious. They inhabit depths where sunlight never penetrates, where pressure is immense and food is scarce. Their elongated tentacles apparently trail along the bottom, detecting prey through touch in the absolute darkness. Most of what we know about them comes from brief video encounters, glimpses of pale arms waving slowly in the beam of a submersible's lights before the creature vanishes back into the black. The deep ocean, covering most of Earth's surface, remains less explored than the surface of Mars, and discoveries like the bigfin squid remind us how much we still don't know about life on our own planet. Life achieves scale in unexpected ways. While individual organisms are usually small, some species create structures of vast extent. A single fungus in Oregon spans over 2,385 acres, possibly the largest organism on Earth by area. This is a honey fungus, Armillaria solidipes, whose body consists mainly of thread-like structures called hyphae that spread through the soil, feeding on tree roots. What appears above ground as multiple mushrooms are actually fruiting bodies of a single interconnected organism. Genetic testing confirmed that this vast network is all one individual, possibly thousands of years old. It's difficult to wrap our minds around an organism measured in acres, a single life form that spans an area larger than many farms. Fungi challenge our usual concepts of what an individual organism is, existing mostly underground or within other organisms, only occasionally producing the visible mushrooms that we typically think of as the fungus itself. Even networks of separate individuals can achieve remarkable scale. Underground fungal networks can exceed the size of cities, connecting different trees and plants in what scientists sometimes call the Wood Wide Web. These mycorrhizal networks form partnerships with plant roots, trading nutrients. The fungus provides the plant with phosphorus and nitrogen extracted from the soil, while the plant provides the fungus with sugars produced through photosynthesis. But the networks do more than just link individual plants to fungi. They connect multiple plants together, allowing them to share resources. A large tree in full sunlight might transfer some of its excess sugars through the network to a younger tree growing in shade. When one tree is under attack by insects, it can send chemical warning signals through the fungal network to neighboring trees, which respond by increasing their production of defensive compounds. These networks make forests more resilient and interconnected than we once realized, transforming our view of forests from collections of competing individuals to cooperative communities. Above ground, animals create spectacular displays through collective behavior. Bird flocks can become so dense they resemble clouds, darkening the sky as millions of individuals move together in coordinated flight. Starling murmurations, those swirling, shape-shifting masses of birds that flow across the evening sky, contain thousands or tens of thousands of individuals following simple rules that create complex collective patterns. Each bird adjusts its flight based on the position and movement of its 7 nearest neighbors, and this simple algorithm generates the mesmerizing displays that seem almost choreographed. Historically, passenger pigeon flocks in North America were even more spectacular, sometimes containing billions of birds and taking hours to pass overhead. Sadly, the passenger pigeon was hunted to extinction in the early 20th century, a reminder that even species that seem superabundant can be vulnerable. But other species still create these dense gatherings, offering glimpses of what Earth must have looked like when animal populations were even larger than today. Looking back deep into Earth's history raises fascinating possibilities about how different our planet might once have looked. Microbes once may have tinted Earth purple, rather than the green we associate with photosynthetic life today. Before chlorophyll-based photosynthesis became dominant, some scientists theorize that early photosynthetic organisms might have used different pigments that absorb different wavelengths of light, possibly giving them purple or reddish colors. These organisms might have dominated Earth's oceans and coasts for a time, creating a world that would have looked alien to our eyes. Evidence for this comes partly from modern purple bacteria that still exist today, using pigments called retinol to capture light energy in a simpler, though less efficient, process than chlorophyll-based photosynthesis. If we could travel back billions of years in a time machine, we might find a purple planet instead of a blue-green one, its color reflecting the particular solutions to energy capture that evolution had found by that point in Earth's history. The green world we know emerged later, as organisms evolved the more complex but more efficient chlorophyll system that now dominates. The tallest mountain on Earth, that iconic peak that has drawn climbers and dreamers for generations, is still growing. Mount Everest grows about 4 millimeters taller each year, pushed upward by the ongoing collision between the Indian and Eurasian tectonic plates. India, once a separate landmass drifting northward across an ancient ocean, began colliding with Asia roughly 50 million years ago. That collision continues today, with India pushing northward at about 5 centimeters per year, crumpling the crust and building the Himalayan mountain range. 4 millimeters of growth per year doesn't sound like much, barely the thickness of a few sheets of paper, but over millions of years these tiny increments add up. The Himalayas are among Earth's youngest major mountain ranges, still rising, still being built by forces deep within the planet. Eventually, erosion and the shifting of tectonic forces will slow and reverse this growth, and the Himalayas will begin wearing down as all mountains eventually do. But for now, Everest and its neighboring peaks continue their slow climb toward the sky. The collision that built the Himalayas also created another remarkable feature. The Tibetan Plateau, sometimes called the roof of the world, stretches across an area roughly half the size of the contiguous United States, with an average elevation above 15,000 feet. This vast elevated region stores the largest freshwater reserve outside the poles, locked in glacier, snowpack, and permafrost. Rivers rising on the plateau, including the Yangtze, Yellow, Mekong, and Ganges, provide water for billions of people across Asia. The plateau's glaciers have earned it the nickname the Third Pole because of the immense amount of ice they contain. Climate warming threatens these ice reserves, with glacier retreating at accelerating rates. The water stored in the Tibetan Plateau doesn't just matter locally, it's crucial to the water security of a substantial fraction of humanity. Changes to this high-altitude reservoir will ripple across entire nations downstream. Beyond storing water, the plateau shapes weather across an entire continent. It also strongly influences Asian weather patterns, acting as a barrier to air masses and driving the monsoon circulation that brings seasonal rains to South and Southeast Asia. In summer, the high plateau heats up, creating a low-pressure system that draws moist air northward from the Indian Ocean, bringing the monsoon rains that agriculture depends on. In winter, the pattern reverses, with cold air flowing southward off the plateau. Without the Tibetan Plateau, the Asian monsoon would be much weaker or might not exist at all, fundamentally changing the climate across half of Asia. The plateau also affects atmospheric circulation on a global scale, influencing the jet stream and weather patterns far beyond Asia. It's a striking example of how solid Earth features, the mountains and plateaus built by plate tectonics, shape the atmosphere and climate in profound ways. Plate tectonics doesn't only create mountains where plates collide. Deep within Earth's mantle, hot rock occasionally rises in plumes, creating volcanic hotspots like Hawaii far from any plate boundary. These mantle plumes are like blowtorches underneath the moving tectonic plates, burning through the crust to create volcanoes. The Hawaiian Islands formed as the Pacific Plate moved over one of these hotspots, with each island representing the location where the hotspot broke through the surface at a particular time. The Big Island of Hawaii, with its active volcanoes, sits over the hotspot now. To the northwest, older islands mark where the hotspot was millions of years ago, each island a snapshot of the plate's position at the moment that volcano formed. Beyond the current islands, a chain of underwater mountains called the Emperor Seamounts continues the trail even farther northwest, showing where the hotspot was tens of millions of years ago. This chain of volcanic islands and seamounts traces the movement of the Pacific Plate like breadcrumbs marking a path across the ocean floor. That movement continues today at a pace we can measure. Hawaii moves about 7.5 centimeters closer to Japan each year, carried along on the Pacific Plate as it drifts westward. Eventually, tens of millions of years from now, Hawaii will be carried beyond the volcanic hotspot that created it. Its volcanoes will go extinct, and erosion will begin wearing the islands down. New islands will form to the southeast over the hotspot's current position. This process has been repeating for at least 70 million years, creating the long chain of Hawaiian islands and emperor seamounts. The bend in this chain, where the islands stop running northwest and begin running west, marks a change in the Pacific Plate's direction of motion about 43 million years ago. Reading the geology of these islands and seamounts gives us a history of plate motion preserved in volcanic rock, a record of the planet's restless surface written in stone and coral. Hawaii isn't unique in its motion. All continents and ocean floors drift at speeds of 1 to 10 centimeters per year, about as fast as fingernails grow. The Atlantic Ocean widens by a few centimeters each year as new seafloor forms at the mid-Atlantic ridge and spreads outward, pushing the Americas away from Europe and Africa. The distance from New York to London increases by about an inch per year. Meanwhile, the Pacific is shrinking as its edges are consumed in subduction zones where oceanic crust slides beneath continents. California's San Andreas fault marks where the Pacific Plate slides past the North American Plate, carrying Los Angeles northward towards San Francisco at about 5 centimeters per year. In roughly 15 million years, if current motions continue, Los Angeles will be adjacent to San Francisco. These continental drift speeds seem impossibly slow from a human perspective, yet over geological time they completely reshape the planet's surface, closing oceans and opening new ones, building mountain ranges and tearing continents apart. The continents haven't always been arranged as they are today. Supercontinents like Pangaea formed and broke apart repeatedly throughout Earth's history, following a cycle that takes hundreds of millions of years. About 300 million years ago, most of Earth's land was joined in Pangaea, a single vast continent stretching from pole to pole, surrounded by a global ocean called Panthalassa. Pangaea began breaking apart roughly 200 million years ago, splitting first into Laurasia in the north and Gondwana in the south, then fragmenting further into the continents we know today. But Pangaea wasn't the first supercontinent. Before it came Rodinia, which formed about 1 billion years ago and broke apart around 750 million years ago. Before Rodinia there were others, their names less familiar: Nuna, Kenaland. The continents are like puzzle pieces that drift apart and then, hundreds of millions of years later, collide again in different configurations. Some geologists predict that in about 250 million years, the current continents will merge again into a new supercontinent, sometimes called Pangaea Ultima or Amasia, though the details of its configuration remain uncertain. When tectonic plates suddenly slip, releasing accumulated stress, the results propagate across the entire planet. Earthquakes send seismic waves through the entire planet, traveling through rock, mantle, and even the liquid outer core. There are several types of seismic waves, each traveling at different speeds and taking different paths through Earth's interior. Primary waves, or P waves, are compressional waves that travel fastest and can pass through both solid and liquid. Secondary waves, or S waves, are slower shear waves that can only travel through solids. When a major earthquake occurs, seismometers around the world detect these waves, and the timing and characteristics of the arrivals tell us about both the earthquake and the Earth's interior structure. It's through studying seismic waves from thousands of earthquakes that scientists discovered Earth's layered structure, identified the liquid outer core, and mapped density variations in the mantle. Every earthquake is a natural experiment that illuminates the planet's hidden interior. Human activities also reshape Earth's surface in ways that become visible over time. Groundwater extraction causes land to sink by up to 1 meter per year in some regions, a process called subsidence that occurs when water is pumped out faster than it's replenished. The ground above compacts as water-saturated sediments lose their supporting pore water, causing the surface to drop. In some parts of California's Central Valley, the land has sunk more than 30 feet over the past century due to agricultural groundwater pumping. Parts of Mexico City, built on an ancient lake bed, have subsided dramatically as water has been extracted. Shanghai, Jakarta, Bangkok, and many other cities face similar problems. Subsidence can damage buildings and infrastructure, increase flood risk, and is largely irreversible once the sediments compact. It's one of many ways that human activities alter the physical structure of the planet itself, changes that will persist long after the pumping stops. Deep in Earth's crust and mantle, certain elements are rare because of how Earth formed. Iridium is rare on Earth but common in asteroids, because iridium is a dense metal that mostly sank to Earth's core during the planet's molten phase. What little iridium remains in the crust came from later additions after Earth had cooled and differentiated. This scarcity makes iridium useful as a tracer for extraterrestrial material. When geologists found a thin layer of clay rich in iridium in rock 66 million years old, deposited right at the time the dinosaurs went extinct, it was strong evidence for an asteroid impact. Iridium from the asteroid was spread around the world in the dust cloud from the impact, settling out to create this distinctive marker layer. Similar iridium enrichments appear at other points in the geological record where impacts are suspected. It's remarkable that an element's rarity in Earth's crust, ultimately caused by planet formation processes billions of years ago, provides the key evidence for understanding catastrophic events that shaped the history of life. Deserts, those vast expanses of sand and rock where rainfall is scarce and life clings to existence in harsh conditions, aren't static features frozen in place. The Sahara Desert expands by about 1 kilometer per month along some of its southern edge, a process called desertification where semi-arid lands gradually transform into desert. This expansion results from a combination of natural climate cycles and human activities like overgrazing, deforestation, and unsustainable farming practices that degrade the soil and vegetation. The Sahel region south of the Sahara, a transitional zone between desert and savanna, has experienced decades of drought and land degradation, pushing the desert boundary southward. In some years, the Sahara actually shrinks slightly during wetter periods, but the overall trend in recent decades has been expansion. Communities living along this shifting boundary face the loss of productive land, forcing them to adapt or migrate. It's a reminder that Earth's climate zones aren't fixed boundaries but dynamic systems that respond to both natural variations and human influence. Among all Earth's deserts, one stands out for its extreme aridity. The Atacama Desert in Chile is the driest place on Earth, with some weather stations in its core having never recorded rainfall in decades of operation. The average annual rainfall in the driest parts is less than 1 millimeter, essentially zero. Parts of the Atacama are so dry that they resemble Mars more than typical Earth landscapes, with soil chemistry and lack of organic matter similar to what rovers have found on the Red Planet. NASA has tested Mars rovers in the Atacama because the conditions are the closest Earth analog to Martian surface conditions. Yet even here, life persists. Bacteria live in the soil, extracting moisture from fog that drifts in from the Pacific Ocean. When rare rain does fall, perhaps once in a decade, dormant seeds suddenly germinate and the desert briefly blooms with wildflowers before returning to its usual barren state. The Atacama's extreme dryness comes from its location between the Andes Mountains to the east and the Chilean coastal range to the west, both blocking moisture, combined with a cold Humboldt current offshore that creates stable atmospheric conditions preventing rain. Earth's surface isn't flat and uniform but varies dramatically in elevation, from mountain peaks reaching nearly 9 kilometers above sea level to depressions below sea level. The Dead Sea, lying on the border between Israel and Jordan, is the planet's lowest land point at about 1,400 feet below sea level. This salt lake sits in a depression created by tectonic forces, specifically the motion along the Dead Sea Transform Fault where the Arabian Plate moves northward relative to the African Plate. Water flows into the Dead Sea from the Jordan River and smaller streams, but with no outlet, water leaves only through evaporation. The intense evaporation in this hot, dry climate concentrates salts and minerals, making the Dead Sea nearly 10 times saltier than the ocean. The water is so dense with dissolved minerals that swimmers float effortlessly on the surface. The shoreline continues to drop as water is diverted from the Jordan River for agriculture and drinking water, lowering the Dead Sea's level by more than a meter per year in recent decades. Within a century, if current trends continue, the Dead Sea could shrink to a fraction of its current size. The interaction between ocean and land creates daily rhythms visible along every coast. Earth experiences roughly 100,000 tidal floods annually, events where high tides push water inland beyond normal boundaries, flooding coastal areas. These aren't disasters in most cases, but natural occurrences that happen predictably based on tidal cycles. During spring tides, when the sun and moon align and their gravitational pulls combine, high tides reach higher than usual. In low-lying coastal areas, particularly those with funneling geography that amplifies tidal range, these high tides can flood streets, seep into storm drains, and temporarily inundate areas that are normally dry. Places like Miami, Venice, and many Pacific islands experience regular tidal flooding that's increasing in frequency as sea levels slowly rise. What used to be rare extreme high tides are becoming more common, a preview of what permanent inundation might look like if sea levels continue rising. These tidal floods are separate from storm surge flooding, which is driven by severe weather rather than astronomical tides, though the two can combine during coastal storms to create especially damaging floods. Nature sometimes defies our expectations in delightful ways, even in something as simple as botanical classification. Bananas are berries, but strawberries are not, at least according to botanical definitions. A berry, in botanical terms, is a fruit produced from a single flower with one ovary where the entire ovary wall ripens into an edible layer. Bananas fit this definition perfectly. Each banana develops from a single flower, and the entire fruit comes from the ovary. Strawberries, despite their name, are not berries but aggregate accessory fruits. The red fleshy part we eat isn't fruit tissue at all but swollen receptacle tissue, and those tiny seeds on the outside are actually individual fruits called achenes, each containing a seed. By the same botanical logic, grapes and tomatoes are berries, while blackberries and raspberries are not. These classifications can seem counterintuitive because botanical terminology doesn't always align with culinary usage. But they reflect real differences in how these fruits develop, differences that matter to botanists even if they don't change how delicious a strawberry tastes on a summer day. The sky sometimes delivers unexpected precipitation beyond the usual rain, snow, and hail. Rib-bit rain events have dropped frogs from the sky in documented cases throughout history, though such events are rare and localized. Strong updrafts in severe thunderstorms can lift small, light animals like frogs high into the atmosphere, carrying them miles from where they started before depositing them elsewhere as the storm dissipates. Historical records describe rains of fish, frogs, and even small birds, events that seemed miraculous to witnesses who couldn't imagine how aquatic or terrestrial creatures ended up falling from clouds. Modern meteorology explains these events as the result of waterspouts or tornadoes passing over bodies of water or wetlands, sucking up whatever they encounter and carrying it aloft. The creatures eventually fall back to Earth, sometimes quite far from their origin, sometimes still alive if the journey wasn't too violent or prolonged. While dramatic, these events don't happen often, and most rainstorms deliver only water. But occasionally, nature reminds us that the boundary between earth and sky is more permeable than we usually imagine. Volcanic eruptions can do more than spew lava and ash. Under the right circumstances, they can preserve entire ecosystems in exquisite detail. Earth once preserved entire forests under volcanic ash, like the 300-million-year-old Wudar forest discovered in China, creating time capsules that show us ancient ecosystems exactly as they existed before being buried. The Wudar forest was buried rapidly by volcanic ash during the Permian period, before the dinosaurs existed, when the world was very different. The ash preserved not just the trees but also their positions, allowing scientists to map the entire forest layout, showing where different species grew and how they were arranged relative to each other. It's like a photograph of an ancient forest frozen in stone. Similar preservation has occurred elsewhere, like at Pompeii where volcanic ash preserved a Roman city, or in Yellowstone where petrified forests show multiple burial events stacked atop each other. These catastrophic preservation events are tragic for the organisms buried but invaluable for scientists trying to understand past ecosystems. While Earth's weather can be dramatic, it lacks some of the more exotic phenomena found on other worlds. Diamonds rain on gas giants like Jupiter and Saturn, but not on Earth. On these giant planets, extreme pressures and temperatures deep in the atmosphere can transform methane into carbon, which crystallizes into diamonds that then fall toward the planet's core like glittering hail. Conditions in Earth's atmosphere never reach the extremes needed for this process. Our planet's diamonds form deep underground, typically more than 100 kilometers down, where pressures and temperatures are high enough to crystallize carbon into diamond structure. Volcanic eruptions occasionally bring these diamonds to the surface in special rock formations called kimberlite pipes. But they form in the solid Earth, not in the atmosphere. Each planet and moon has its own unique combination of conditions, creating phenomena that would seem fantastical if we encountered them anywhere but in the place they naturally occur. Earth's geological activity keeps its surface relatively young and dynamic, avoiding the ancient, static landscapes seen on smaller worlds. Earth avoids crust-bending extremes seen on Mars, where the Tharsis volcanic region created such massive weight that it literally tilted the planet's entire crust. The Tharsis Bulge, containing several enormous shield volcanoes including Olympus Mons, the largest volcano in the solar system, represents so much mass in one location that it deformed Mars's shape and may have caused the entire crust to shift relative to the planet's rotation axis. Earth's plate tectonics prevent such extreme concentration of volcanic activity. Instead of building one enormous volcanic pile, Earth distributes volcanism across many plate boundaries and hotspots. The continents move, spreading volcanic activity over wide areas and over time, preventing any single region from becoming so volcanically massive that it warps the entire planet. This is another way that plate tectonics makes Earth different from smaller, geologically simpler worlds where one or a few large features can dominate the entire surface. Beneath our feet lies a complex and varied layer that we often take for granted. Earth's pedosphere, the soil layer that covers much of the land surface, contains over 3,000 distinct soil types, each with unique properties determined by parent rock, climate, vegetation, topography, and time. Some soils are rich in organic matter, dark and fertile, perfect for agriculture. Others are thin and rocky, barely covering the bedrock beneath. Some are acidic, others alkaline. Some hold water well while others drain rapidly. The diversity of soils reflects the diversity of environments where they form and the different processes that create them. Soil isn't just dirt, it's a complex mixture of mineral particles, organic matter, water, air, and living organisms including bacteria, fungi, insects, and worms. A handful of healthy soil contains more organisms than there are humans on Earth. Soil takes centuries or millennia to form through the weathering of rock and the accumulation of organic matter, yet it can erode away in years if vegetation is removed and it's exposed to wind and rain. Agriculture depends entirely on soil, making its preservation one of the critical challenges of feeding a growing human population. When we step back and look at Earth as a whole, what emerges is not a collection of separate parts but an integrated system where everything connects. Earth's biosphere, atmosphere, hydrosphere, and lithosphere work together as a single system, each component influencing and depending on the others in countless ways. Life affects the atmosphere, as we've seen with oxygen-producing photosynthesis transforming the air over billions of years. The atmosphere affects the hydrosphere, carrying water vapor that becomes rain and snow. Water shapes the lithosphere through erosion and weathering, carving canyons and wearing down mountains. The lithosphere influences life by providing nutrients and creating diverse habitats. Plate tectonics drives volcanism that replenishes atmospheric gases. The cycling of elements between these spheres, carbon moving from atmosphere to ocean to rock and back again, water evaporating and condensing and flowing, nutrients moving from soil to plants to animals and back to soil, all these cycles interlock and depend on each other. Scientists sometimes call this integrated system the Earth system, recognizing that you can't truly understand any one part without considering how it fits into the whole. Changes in one sphere ripple through the others, which is why understanding climate change or biodiversity loss requires looking at the entire planet as a connected whole. When we consider what makes Earth special, what allowed it to become a living world teeming with complex organisms, several factors stand out as essential. Without plate tectonics, stable climate, and liquid water, complex life would not exist, at least not in the forms we see today. Plate tectonics recycles nutrients, regulates atmospheric carbon dioxide over geological timescales, and creates diverse environments from deep ocean trenches to towering mountains. The stable climate, held within habitable ranges by various feedback mechanisms including the carbon cycle, allowed lifetime to evolve complexity without being reset by extreme swings between heat and cold. Liquid water serves as the medium for biochemistry, the solvent in which the reactions of life occur, and the transport system that moves nutrients and waste. Remove any of these three factors and Earth would likely be a sterile world, perhaps with simple microbial life in isolated pockets, but nothing approaching the forests and coral reefs and herds of animals that characterize our planet. We're still discovering planets around other stars, searching for worlds with similar characteristics, but so far Earth remains unique in our experience, the only place we know for certain where all the necessary conditions came together. The more we study Earth and compare it to other worlds, the more we appreciate how many factors had to align just right. Earth's magnetic field, chemistry, and orbit create a rare planetary balance that may be uncommon in the universe. The magnetic field shields the atmosphere from being stripped away by solar wind, allowing air to persist over billions of years. The chemistry, with abundant water, carbon, and other elements necessary for life in forms organisms can access, provides raw materials for biology. The orbit, circular enough to avoid extreme seasonal variations, tilted enough to create seasons but not so tilted as to create uninhabitable extremes, at just the right distance from a star of just the right size and stability, all of this creates conditions where life can not only begin but persist and diversify. We don't yet know how rare these conditions are. Perhaps Earth-like planets are common and we simply haven't found them yet because they're far away and hard to detect. Or perhaps we're unusually fortunate, living on a world that won the cosmic lottery. Either way, understanding what makes Earth habitable helps guide our search for life elsewhere and deepens our appreciation for the world we have. For all our exploration and scientific advancement, Earth still holds immense mysteries close. Despite exploration, over 70% of Earth's surface remains unexplored in any detailed way. This is largely because 70% of the surface is covered by ocean, and most of the ocean floor has never been directly observed by human eyes or even mapped at high resolution. We have better maps of Mars than of most of Earth's seafloor. The deep ocean remains largely unknown, with new species discovered on virtually every expedition to the abyss. But even on land, vast areas remain poorly explored. Remote rainforests harbor species unknown to science. Cave systems extend for miles underground, most of them unmapped and unvisited. The soil beneath our feet contains microbial diversity we're only beginning to catalogue. Even in well-studied regions, new discoveries happen regularly. Just in the past few decades, scientists have found previously unknown species of large mammals, entire ecosystems thriving around deep-sea hydrothermal vents, and bacteria living miles beneath the surface in solid rock. Earth continues to surprise us, revealing new wonders to those patient enough to look carefully. As we drift towards sleep, it's comforting to remember that Earth remains dynamic, evolving, and full of unanswered mysteries. The planet that exists today is not the planet that existed a billion years ago and will not be the planet that exists a billion years from now. Continents will continue their slow dance across the surface. Species will evolve and go extinct. Climates will shift. The story of Earth is not finished but ongoing, a narrative still being written by geological forces, biological evolution, and increasingly by human choices. There's something deeply satisfying about living on a world that still has secrets, still has unexplored corners, still can surprise us with discoveries that challenge our understanding. As you close your eyes tonight, you're resting on a planet that's spinning through space at incredible speeds, that's made of ancient stardust, that hosts millions of species, most of which remain unknown, that generates its own magnetic field from swirling liquid metal thousands of miles below, that has existed for 4.5 billion years and will exist for billions more. You're part of this remarkable system, connected to everything from the deepest ocean trench to the highest mountain peak, breathing air produced by microscopic ocean plants, drinking water that cycled through clouds and rivers and ancient glacier. Earth is your home, dynamic and ancient and precious, still revealing its secrets to those who take time to listen and observe. Rest well on this pale blue dot, this improbable paradise floating in the cosmic dark, this living world we call home.